Hi, this will be a video on the conservation of total mechanical energy. So this just means that in a closed system, we can't have energy created or destroyed, or in other words, the total energy at time 1 is also equal to the total energy at another point in time 2. So you can also expand on this by saying that the sum of potential energy, kinetic energy, and spring potential energy would be the same at any point in time. For example, if we disregard spring potential energy just for now, a decrease in potential energy would increase or result in an increase in kinetic energy, since the energy in this closed system is conserved, or you can just say the total energy is constant. So such a process is considered an energy transformation and requires an action of a force to occur. Okay, let's start an example here. So say we have an object with a mass of 2 kilograms, 5 meters above the ground. And we'll treat downward as positive here. We have an initial velocity of 2 meters per second going downwards. And we have gravity equaling to 10 meters per second squared, just for simplicity. Now, what would the total energy of the system be initially? So the total energy is defined as the sum of potential energy and kinetic energy, where potential energy is mg delta h, and kinetic energy is half mu squared. Alright, so we'll treat the ground as our reference height, or in other words, where h is equal to 0. So the change in height where the object is and the ground would be 5 meters, or in other words, delta h is 5. So let's plug that in along with m and g. And we also given u as well, so we can find out what our kinetic energy is. Doing the math here would give us a total energy of 104 joules initially. Okay, so let's try to find its speed right before this object hits the ground. So the total energy is equal to potential energy plus kinetic energy again, except we also know that the total energy remains constant, so we can use our value of 104 joules as our total energy. Okay, so potential energy is mg delta h. Alright, so delta h here would actually be 0, because the difference between the object and the ground would be 0 right when it's about to hit the ground. And then we have our kinetic energy of half mv squared, where v would be our final velocity. Doing a bit of algebra here to rearrange for v, and this would give us v equaling to root 104, or our velocity would be approximately 10.2 meters per second. Okay, so in this second example, suppose we have a mass that's attached to a spring, and this mass is to travel up this slope to the right after it's released from the spring. And we'll treat the reference height as where the ground is. As the ground where the mass is lying on. And that will be where h is equal to 0. So we know that this mass has a mass of 5 kilograms and it's pulled back 1.5 meters onto a spring, where the spring's constant is 200 newtons per meter. So first of all, the mass is held at rest at this point and then released. Okay, so first of all, let's work out the velocity of the block as it just leaves the spring. So we know that the total energy is just equal to its spring potential energy, half k delta x squared. Now, this is because the gravitational potential energy would be 0 since it's still on the ground, so there's no change in height. Additionally, we also know that when we stretch it back, we're holding it at rest initially. So when it's at rest, velocity is 0, no kinetic energy. So spring pulled back 1.5 meters from relaxed state, delta x would be equal to 1.5 meters. So it's really important to point out that delta x is just the change in length of the spring, and it's not to be confused with anything like the length of the spring or whatnot. Okay, so we'll plug in the numbers here. K is the spring constant of 200, delta x is 1.5 meters, and and this would give us a total energy of 225 joules for this closed system. Okay, so now we have to equate this total energy to the kinetic energy right as it leaves the spring. So right when it leaves the spring, the change in length of the spring would just be 0 because the spring is back to being in its relaxed state. And gravitational potential energy, of course, is still 0 since this mass is still on the ground. So now we just have this unknown velocity, but it's still moving, right? So there's kinetic energy, so that's half mv squared, and that's equal to our total energy. Okay, so on the right hand side we know our mass of 5 kilograms, but we don't know velocity. We also know that the total energy doesn't change since it's conserved, and that's 225 on the left side. Rearranging from v here will give you this surd here, which will approximate our velocity to 9.49 meters per second. Okay, so since this mass is moving to the right, it will eventually reach the slope. And you might be wondering, what is the maximum height the block will travel up the hill? Well, first of all, we know our total energy is 225 joules, and we know that when it moves up the hill, the change in height of the object relative to the ground will change as well. And when it's at its maximum height, the instantaneous velocity at that point will be 0 meters per second. Okay, so we don't have any velocity, so there's no kinetic energy, and there's no spring potential energy, of course. So we're just left with our potential energy, defined as mg delta h. So we'll just simplify delta h as h here, since our reference height is 0. Okay. So the total energy on the left is 225. We know our mass of 5 kilograms, and g is 10 meters per second squared. So working out h here will just give us 4.5 meters. That's how high it will be above the ground. Thanks. So this will be the end of this video on conservation of total mechanical energy.